All right, last chapter, sequences and series, and it's mostly series. Let's do a little notation real quick. When you have a sequence, it means that you've got a comma between the term and the next term. So a very famous sequence, the counting numbers. And a lot of times you need a general term for a sequence. We use little n a lot. So does your calculator, which we'll see way down the road. And anyway, so let's look at a famous sequence. What about this sequence? And that's the Fibonacci sequence, and they write it like this. They write a little recipe for it. So here's a Fibonacci sequence. It starts with a pair of ones. So the first Fibonacci number, and this is just typical math notation. F just stands for Fibonacci. It isn't function or anything like that. It doesn't have any math weight attached to it. But the subscript tells us the position in the sequence. So the first number is a 1, the second number is a 1. And then to get the third number, you add the first two. So to get the 8th number, you add the 7th and the 6th number. Do you see? If I want the 8th number, then n is 7. 7 minus 1 is 6. So the f sub 8 is f sub 7 plus f sub 6. So the book gives you little recipes in the first section. No big deal. Just be able to read sequences and be able to use recipes to make the sequence. So you can still take a limit of a sequence if you happen to have things like, let's say we have a sequence where a sub n is equal to n squared minus 1 over n squared plus 1, and n starts with 1. Let's just say, so what's the limit of this sequence as n approaches infinity? Well, that's just the limit of n squared minus 1, n squared plus 1, and you can see the n squareds are battling it out. The limit is 1. So they'll ask you questions like that. Not the biggest deal because most of the chapter is series. So let's see what a series looks like. A series has plus signs in between. So you have a sub 0 plus a sub 1 plus a sub 2 plus dot 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 plus a sub n plus dot dot dot. So we've come to our first philosophical question. The Greeks were aware of this question. They were aware of the following problem. They weren't sure what to make of it because there was the common sense and then there was the philosophical, which we'll get to. So let's say we take a square. It's a 1 by 1. What's the area? Eric. And Eric says the area of this square is 1. Okay, so Kyle, I cut this square in half. What is the area of this? And Kyle says 1/2. And then we take the remaining 1/2, and I'm going to ask, let's ask Bree, because she's going to be a teacher when she grows up. I cut this in half. What is this area? And Bree says, that's easy, Dr. McDaniel. That's a 1/4. And I say, thank you for using my honorific because I have a PhD. Very nice. Anyway, so that's a 1/4, and you can see it. It's a 1/4 of the original thing. Okay, so Rose, what's this area? And Rose, being a future teacher, quickly calculates and says, okay, that's half of a 1/4, that's an 1/8. Good. John, half of that, 1/16. Megan, what's half of 1/16? 1/32. Half of that, 1/64. You see where I'm going? The Greeks wondered, what about this? What if I have 1/2 plus 1/4 plus 1/8 plus 1/16 plus the rest of the gang, and I wonder what that all equals. The infinite sum. Can we add these up? And you can see all we're doing is getting this sum. You know, we're just constantly cutting stuff in half and working our way down. We'll never leave this square, but what we will do is we'll fill it in. So the infinite case should be 1. But there was a philosophical question because the Greeks, you know, they thought about this stuff really hard. And one of the philosophical question was this: how do you know? I mean, we have a picture, it's convincing, but you can't just add these up because you'd never finish. So how do you write this and consider it as a math proposition, as a math thing to do if it doesn't have an end? And the productive mathematicians, the ones that went on to develop all their big ideas in geometry and measurement and calculations and curves, all the stuff they're doing, we don't have a problem with this. We don't have a problem with it. It's not like I'm taking control of infinity. I am a god. I'm just saying, look, I see a pattern and I can do the pattern. Now this philosophy held for a long time. And then there was the case of, we'd like to be able to have a math reason that's a closed reason, like a convincing reason. So let's do this. Let's pretend we don't know what this sum is. We're just going to call it S. I'd like to find what that sum is. So I don't think any of you have taken discrete math yet, but this is a trick you learn in discrete math. It is a classic. I mean, this is older than dirt. So we pretend we don't know what this sum is, and we call it S. And then what would 2S be? Now I didn't pick this 2 out of thin air. I happen to be dividing by 2 each time. So if I do 2S, that would be 2 times a half, that's 1. 2 times a fourth, that's a half. 2 times an eighth, that's a fourth. Do you see I'm recreating the series that I had with an extra 1 in front. Does anybody see the move? Does anybody see the move? And Becca says, I see the move. Good job, Becca. What are you doing? She says, we'll do 2S minus S. And that's the same as this whole sequence minus this whole sequence. And just look at it. This top series minus this bottom series. The halves cancel. The fourths cancel. The eighths cancel. The 16ths cancel. Everybody cancels except this front letter 1. And what's 2S minus 1S? It's S. S equals 1. The sum is 1. That's actually acceptable. There is a little bit of extra hooky dooky to worry about, which we'll get to way later. But I'd like to show you where the hooky dooky comes from. What if you got 1 minus 1 plus 1 minus 1 plus 1 minus 1 plus 1? What if you did this? Does this add up to 0? Or does it add up to 1? Because you can say, okay, I'd like to keep this 1 and have these 2 1s cancel. And then these 2 1s cancel, and these 2 1s. So the sum is 1. And you say, well, hey, you got an infinite supply of minus 1s. Why don't you shove 7 positive 1s to the front and let everybody else cancel? So now the sum is 7. And the math people think, oh, crap. How do you know when you move the pieces around and do the hooky dooky that we're doing? And we will learn. We will learn how that there's actually a set of rules on when you can do little tricky moves. But it's going to take a while to get there. But we will get there. All right, so this is the kind of problems you should be able to do. And this kind of series, where you're adding an amount, you have a starting amount, and you multiply by a fraction. That kind of series is called geometric series. You should be able to do one. It's an important idea. So geometric series is of the form A plus A times R plus A times R squared plus A times R cubed plus dot, 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 dot. Now, if you only do a finite geometric series, then you don't have the dot, dot, dot. You stop somewhere. And there's a formula for that. It's not as famous as the formula we're about to get. I'd like to get this formula. But I need, let's call it S, but I need to know that these numbers are getting smaller. So there is a rule for geometric series. I need the absolute value of R to be less than 1. If you look at the one that's on the board here, I'm multiplying by a half each time. If you multiply by a number that makes each term smaller, you got a really good chance that everything adds up, and you got a trick to get the sum. You can actually add up an infinite number of things and get a finite sum. So if I'm multiplying by a ratio, that's what that little r stands for, of less than 1, these terms are getting smaller. So they fit into some kind of little box, like a grid like we had before. They get smaller and smaller pieces. What's the area of the whole thing? All right, well, our trick here is, well, let's just do AS. AS would be RS, my fault. RS would be AR plus AR squared plus AR cubed plus AR to the fourth plus the rest of the gang. And now let's do Becca's move there. Let's just subtract these guys. Doesn't matter which way you subtract. If I do S minus RS, I get, okay, A, nothing to cancel with. So let's just leave the A. But I have AR minus AR squared minus AR squared, AR cubed minus AR cubed, etc. Oh, there's nothing else to write. I like it this way. This is good. So now, factor out the S, because we care about it. All right, so the sum is equal to the first term divided by 1 minus R. That is a very cool formula. Let's use it a few times. Let's use it on this one here. When I started with 1/2 plus 1/4 plus 1/8 plus the rest of the gang, my first term was 1/2, and I'm multiplying by 1/2. So my sum is 1/2 divided by 1 minus 1/2. 1/2 divided by 1/2 is 1. We got 1 for that. Let's try another one. Suppose I have a geometric series like this. I start with 10, and I multiply by -1/5. So 10 divided by 5 is 2, but I get a -2. What's -2 times -1/5? That's a positive 2/5. Next one's going to be a minus 2/25. So this is called an alternating series. And this guy gets small really quick. Look at how teeny those pieces get. And according to my formula, this sum is equal to the first term, which is a 10, divided by 1 minus -1/5. Let's just stop there and appreciate what just happened. 10 divided by this, I'm going to have 1 plus 1/5 down there. My denominator's big, which makes my sum small, which makes sense because it starts with subtraction. I have 10 minus something. So I'll never get back up to 10, will I? In fact, it's 10 minus 2. I'm never going to get back up to 8. You know, well, I'll get a little bit above 8 and then subtract some more off. You know? So it's going to stick maybe around 8. Let's see what happens. So I have 10 divided by, this is 5/5 plus 2/5 is 6/5. That's 50 over 6, otherwise known as 25 over 3. So it's 8 1/3. So yeah, it never gets back up to 8, but it closes in on 8 1/3. So that's what this sum adds up to. So now you can begin to see how the Greeks began to wonder about this. It's like 25 over 3. I'm not sure if I'm seeing it like I did with that 1 by 1 square. But this is this kind of thing. Geometric series gets a lot of press. So go to the first section on series. It's the second section of the chapter. Try some geometric series problems. Then they have a thing called arithmetic series, which is when you add the same amount each time to your series. How are we doing here? Oh, this is too long. All right, so try a few geometric series. See you later.